Thank you. Good afternoon. We are Team UCI. I'm Shan, and I will be the presenter for our project design for this district of University of Central Florida. So our team consists of 4 members. I'm responsible for the battery integration and development plan, and Yanchen focused on the conceptual design, which he did the distribution system analysis, and Hengyi takes charge of the financial analysis. We have 2 advisors, Alex from Tesla and the Professor Jack Brower from UCI. So I will go over the brief, the methodology and the final proposal for this presentation. The UCF sets the campus sustainability goal of reaching carbon neutrality by 2050 and identifies the existence of vacant land or 14 megawatt of solar arrays and battery storage. A future microgrid project is also visioned in the master plan as power sources. So the current load profile is shown in the right with a peak demand of over 8 megawatt. With the information given for this case, we divided our design process to 3 parts. We started by producing the conceptual design with outputs production profiles for the system, and the re-op and SEM are used for determining the optimal PV and battery size. Aurora is used for PV system layout analysis. We then analyze the overflow and upgrade potential for a distribution system by OpenDSS to ensure compliance with the grid constraints. The design results are then integrated into a financial model, which will lead to a final recommendation. So we will walk you through our design process in the following sections, starting with the conceptual system design. According to the Orange County Order of Ordinance, the campus is located in multi-family district and industrial district. Both districts allow rooftop and open space solar installation. We also consider the flood hazard. According to FEMA flood hazard map, our design on rooftop buildings and open land area, both circled in red, are safe from hazards. However, the black circle above is the pond area, which has the potential risk of flooding. Thus, we did not place any floating system over there. So our design of solar system is highly compliant with the university master plan. For example, the parking area in the black circle here is located in red academic area according to the master plan. So we did not place any carport solar structure there in case the lecture hall will be built in the future. An environmental permitting will be needed for the empty land located in the southeast of campus for tree removal. To compensate the impact of the project, agrivoltaics that allow the land to be utilized to grow other vegetations, such as food crops, is proposed as an alternative. So our design covers 15 rooftop buildings, 1 parking structure rooftop, and 2 open space parking lots. In addition, 1 land area will be built with a small solar farm. If we decided to place battery systems, there will be 5 locations as indicated by figure on the right. For the solar system design, we choose Ginger 330 watt monocrystalline solar panel with high efficiency, and the advanced half-cut cell technology to better perform under shading conditions, especially in urban areas. We also choose SunGrow string inverter with capacity range from 44 kilowatt to 250 kilowatt. The PV installation also requires several transformers and overhead services, as shown here. For the battery integration, a 2-hour lithium-ion battery racks from the LG Chem 1000 will be chosen for this project. 2 transformers will be needed to support the battery integration. We use the Aurora Solar to design the PV system. First, we draw the rooftop on Google Image and perform shading analysis to choose the best location to place solar panels. Inverters are then placed near the edge of the roof for easy maintenance and wiring solution. Lastly, a single line diagram for the electrical system is generated. The overall solar design includes 15 buildings, 3 parking spaces, and 1 open land space. And this modeling process results in an on-site system of a total capacity about 8.4 megawatt and an annual production of 12,000 megawatt hour. So the figure on the right-hand side shows that the electricity load on campus will be met by the on-site PV generation and the local utility grid. So solar production will offset about 18% of annual electricity consumption of the entire campus. There is no solar curtailment fund for our design system. Our distribution system impact analysis proved that our PV system can be safely integrated with the grid. We can see from the two figures on the left that power supply and demand has been balanced. And we can also observe that a per unit voltage increase of less than 2%, which is acceptable. So battery is used for shifting the electricity load by charging during the load valley and discharge during the peak load period. The SAM and REOP are used to maximize the system net present value based on the system capital cost, net load, and the PV capacity constraints from the conceptual design. To reduce the maintenance and the replacement of the battery, the depth of discharge will be designed to remain at 70 to 80%. To decide the battery's seating locations, we choose two major areas according to the location of substations. So each area divides the total battery capacity according to their respective overall average load, as shown on the left figure. We also harness the mixed integral linear programming algorithm to optimize the seating. The allocation results are shown on the right. The battery capacity is determined to be 585 kilowatt hour, and with the power capacity of 292 kilowatt. After installing the battery system, we saw an increased imbalance of power supply and demand relationship, as shown on the left. On the right, we can clearly see that the total active power loss increased drastically after installing a battery system. And we believe that the benefits of batteries may not justify the power loss it causes. So we're walking you through the financial analysis. Our assumption includes the cost of system and equipment, utility rate analysis, tax incentives, electricity consumption, then the cash flow analysis and university savings for a business as usual case. A PV system with and without the battery package were calculated. We will then present our final recommendation based on the analysis. So the cost of the PV system will only be around $10.3 million as shown in the right table here actually. And the cost of PV plus storage system will be higher number on the bottom of left table, which is around $12 million. So UCF is currently under GSDT1, and the current utility rate is about 6.5 cents per kilowatt hour, and the demand charge rate is about 28%. The total annual utility cost is about 4.4 million currently. We come up with a PPA price of 6 cents per kilowatt hour based on the current utility rate and the 3% annual escalation. Since the third-party power purchase agreement are currently disallowed under Florida's utility regulation, we calculated a lease price of $76.5 thousand per month based on the lump sum future cash flow generated from the system and divided by a period of 20 years. The project enjoys federal ITC payment program. We use a 5-year Marcos depreciation method as well. So the annual production for a PV-only system will be around 12 million kilowatt hour. With battery, we will have additional 268.6 thousand kilowatt hour per year electricity consumption. So there will be no debt or loan for this project. The cash purchase price is based on the installed cost of the system instead of the expected future value of the energy generated. So we arrive at an $11.3 million project sale price for the PV-only system by comparing the aggregated system cost with a 10% margin to the total cumulative discounted cash flow from the system in a PPA model. For our equity investor, we will have a 5.3 project IRR for the PV system without battery, and the payback period around 12 to 13 years. For the system with batteries, the IRR is lower and the payback period is increased to 13 to 14 years. So the total electricity university saving for the system without battery is about $5 million, which is about additional $600,000 NPV benefits compared to the system with batteries. With that, our final recommendation based on previous analysis is an on-site PV only system with this agreement at a rate of $76,500 per month. The cash purchase price is $11.3 million. The project can deliver an investor IRR of 5.3% and create about $5 million saving over 20 years. The alternative plan is the PV system with batteries, which increase the lease rate to $78,000 per month. And the alternative plan has higher cash purchase price, lower investor IRR, and the customer savings. And for the construction plan, it includes 3 phases: permitting, construction, and interconnection and inspection. The overall construction could take 9 months to a year. So we recommend the campus to start the project as soon as possible so that the actual construction phase can take place in the summer to reduce the impact to the campus operation. And the on-campus solar, we have also identified several strategies to engage the community. The on-campus solar system, which can be used as the educational resource to advocate solar and raise the community interest and awareness. In addition, the Student Association and the Campus Sustainability Center can cooperate to develop solar fact sheet and organize solar workshop or information sections to provide opportunities for students and staff to engage with the project. The University of Central Florida can also develop curriculums around solar energy, battery storage, and other sustainability related topics, and use the on-campus system as hands-on learning materials for students. The carport PV system can be further integrated with electric vehicles in the future. So with that, we want to thank you for your attention, and thank you to the NREL for giving us the opportunity, as well as thank you to UCF for providing such an interesting case for us as a learning material. We will be happy to take any questions.